Raise the roof, roof, roof.
Now we're going to do some simple example problems for Newton's second law. I've already written down our kinematic equations, and yeah, you probably thought we were done with them, but we could also use them for Newton's second law. If you remember, and hopefully you do, F equals ma. Okay. And you'll notice that we have acceleration in our Newton's second law and in every single one of our kinematic equations. So it's the link. I like to refer to the acceleration kind of like time in projectile problems. All right, when you have a projectile problem, what links the x and y directions? It's time. You probably have to find it every time you do a problem. All right, and in this case, our link between our force and our kinematic equations is the acceleration, and you will need it. So let's look at the first example where we have an object, maybe a wagon, maybe just a box on wheels, right, being pushed with a force. We can say that the force is something like 50 newtons. Okay. And maybe the box has a mass, m, equaling 10 kilograms. A question could be, what is the acceleration? I'm going to put a part B down here later, but I don't want you to think about it till we get there. If you look at this, F equals ma. F equals ma. We know the force and the mass, so it's pretty simple to solve for the acceleration. F divided by the mass, which would just be 50 newtons, divided by 10 kilograms, and we would get an acceleration of 5.0 meters per second squared. Okay. The acceleration is in the direction of the force. Okay, that's good, both positive. And we also use the force in the direction of motion, which I'm going to make a more of a point on that later when we get to a problem with an angle. Right? In part B, I want to ask the question, if starting at rest, where is the object after 3 seconds? Okay. So I want to know the displacement after 3.0 seconds. So basically, our cart is going to be someplace over here. Same mass, same force, and we're accelerating the entire time. So we're speeding up. Okay. So if I look at my kinematic equations, I'm looking for x. I said that I started at rest, so the initial velocity would be 0. Make a note of that here. And I'm looking for my displacement, and I have my time. So that leads to the third equation down there, where x equals VIT plus 1/2 AT squared. My initial velocity is 0, and now I could just substitute in my values. Acceleration is plus 5.0 meters per second squared times 3.0 seconds squared. 22.5. Now I wrote down 23 because if we look, we have two significant digits. 5.0 and 3.0, both two significant digits. Well, how about if I wanted to know, we'll do a part C here. How about if I want to know the final velocity at this time? Well, we find an equation that has everything that we know in it. So we can look at the first one. So VF equals VI plus AT. Now there's a reason I also like to pick this one. All right. I don't like to use the second one, this one right here, because we had to solve for x and we had to solve for a. In the top one, we only had to solve for the acceleration. That limits mistakes. So VF is equal to the acceleration, 5, times the time, which is 3.0 seconds. Still two significant digits, and my final velocity would be 15 meters per second. So that's a real simple example of Newton's second law. Now you'll notice, as I'm erasing this, that the time I used was fairly small. Okay? When we have accelerations, typically the times are fairly small. Or I should say forces. When we have forces, the times are fairly small. If you have forces acting over long periods of time, it leads to objects moving extremely fast that sometimes wouldn't make sense. For example, if you have a car, all right, let's say we have a car. Watch my beautiful drawing of a car here. Hopefully you're laughing at this. If we have a car accelerating for like 1 hour. Now, when in the world have you ever been in a car that you've stepped on the gas and actually sped up for an entire hour? No, you step on the gas and you speed up for seconds at a time. Okay? If you were to speed up for an entire hour, you'd be going probably thousands of miles per hour. Okay? Tens of thousands. It just wouldn't make sense. So our forces typically act over short periods of time. Now let's set up one last example problem. In this case, we're going to have our same object, mass equaling 10 kilograms. But now we're going to have the object pulled. Now if the object was pulled in this direction with the same force, 50 newtons, nothing changes, okay? Whether it's push or pulled, it doesn't matter. The net force would be 50 no matter what there. Now the thing that changes though is, let's say we pull this at a force up at an angle. And let's say we still have 50 newtons. Now the difference is, not all of our force is pointing in the direction of motion. So the motion is in this direction. I have to give it some sort of angle here, and let's say that angle happens to be 35 degrees. Okay. The only force I actually care about in this is the force in the x direction. Why? Because it is the force in the direction of motion. So the first thing I have to solve for when I do anything here, like let's say I'm solving for the acceleration. Okay, we're solving for the acceleration. I have to solve for fx first. Right? So fx, and you can look back at the intro videos to the second law, and I talk a lot about how you come up with these. All right, here would be our angle, 35 degrees. It is adjacent, so we would have 50 cosine of 35 degrees. We'd actually get a value of 41. It's something I need. I like to circle it. Right. Now if I were solving for the acceleration, I wouldn't use 50 newtons. All right, that's irrelevant now. I would just use my Fx, 41 newtons. So my acceleration, once again, would be equal to F divided by m. And it would be 41 newtons divided by 10 kilograms. And the result of this makes a lot of sense. Okay. Last time our acceleration was 5 meters per second squared. This time it's 4.1. All right. Now, why does that make so much sense? Well, not all of your 50 newtons is pointing in direction of motion. So only part of it is. So that, therefore, you're going to get less acceleration. Okay. I noticed one thing I did here, and this might actually help you out if you were to write these in. You might want to put x's here. Okay? That may help you know that we're talking about the acceleration in the direction of motion. Okay, so AX. So those are two ways of looking at Newton's second law on flat ground. Okay, they're fairly simple, straightforward examples. In the next example problems that I'm going to do, I'm going to look at stuff on an incline, boxes, sleds. All right, and those are a little more difficult, but still not too bad. Keep looking at the intro videos to the second law, because some of the stuff I kind of go through faster here are in those intro videos, and it'll help it to explain it a lot better. All right.